Okay, we're on the air. For those of you that may watch this later, it took a long time to realize it. The blinds threw me off when I walked in here. That's my excuse. At any rate, we were just talking about optical channels, and this is something I got experience on when I worked in industry down in Scottsdale, Arizona. And my first job was for Motorola Government Electronics, and I worked on a program called LaserCom. And the program LaserCom used green light, and it was free space. It was a very fun project to work on because it tested at the White Sands Missile Range. This was back in the late, well, about 1980, so a long time ago for you guys. You weren't even in existence then, right? But what was cool about it was it transmitted 1 gigabit per second, which is pretty high rate for that time frame. And it did it free space, and it did it in a visible light band. So when it was being tested at night in particular, when I was down there, I was involved with the receiver front end that amplified signals coming from the photomultiplier tubes, which were used to sense the received green laser light through a telescope. The plane that was flying overhead in the missile range sent down the green laser light, and as it came onto this dome, it was just this eerie scintillating green glow that came down. Makes you think of something to do with Martians, right? Mars and green, they kind of are associated, right? And the high data rate signal came down, and part of the demo was to be able to send television channels down, which require a lot of bandwidth. This was before HDTV, so they were sent at full bandwidth. Now, in order to make that link work, though, there was an infrared beacon laser that shot up from the ground station, a very high power infrared, to provide a two-way tracking mechanism to make sure that these telescopes with their gimbals and things would actually stay pointed. Because if you play with the laser pointer, you know how narrow the beam is. It's very narrow. It doesn't diverge very rapidly. And pointing is microradians of pointing accuracy were required to keep the laser spot on the dome of the tracking station. It never got fielded because there were problems with the laser technology itself, but it was a fun project to work on. Fiber optic, though, is very big, and that's what I'm passing around. The single mode fiber is used commonly for the long haul cables back and forth across the country, I think even around town with all the fiber optic they've laid down. The single mode has much less dispersion than the multi-mode fiber does, just like a waveguide would. So it's basically optical fiber is a waveguide for optical frequencies as opposed to microwave frequencies. It's a whole discipline within the communications area that people can go off and study. Wider and wider bandwidth laser devices to put signals into the fibers, and then fiber manufacturer. And I'm sure all of you have seen those trucks with the drilling rigs that kind of angle down into the ground like this. They're usually laying fiber cables down, as far as I know. That is really our source of internet, if you think about it. It's minuscule what the free space can haul in terms of data compared to what a fiber can haul. Fibers are what have made the internet what it is. We also use optical on discs and things too. CD, DVD, Blu-ray, and so on. Switching up to at least look at things at a high-level systems view, we have the OSI, or Open Systems Interconnect model. If you have an interest in that, or maybe you have, you're going to come back and get a computer science degree. A lot of EEs still do that to this day. They come back and make their next degree a computer science degree. There's a networking class that you can take in computer science that basically talks about this model. Where we're at for this class is here. We're entirely in the physical layer. But if you're looking at it in a hierarchy of parts of a standard, then you would go up to the data link layer, and this is pretty much where we fade out. I mean, most of you are familiar with MAC addresses and the MAC idea itself. The media access control is what that stands for. That controls how the upper layers are able to use the physical channel to actually transmit and receive. It brings law and order to things in a sense. If everybody is trying to use the same frequency, there has to be a MAC in there, otherwise everybody would be clobbering each other. So as a physical layer designer, you assume that there's a protocol stack that will have the MAC included in it in terms of how it addresses when to use the channel and when not to use the channel. Has anybody studied any of that in another class or ever read anything on the internet about how some of that works? The simplest models is what Ethernet uses, and it's really not as complicated as you might think it is. I'm trying to remember what, my brain is not thinking of it right now, but the basic idea is you try to send a packet, or you sense if anybody's using the network by listening, and then you jump in to try to send. If you have a collision, then you have random back-off time where you get to try again, assuming that if you collide with another person because they jumped on at the same time you did, they weren't able to discern you were present, you couldn't discern them because you just both came on at the same time, but the users randomly back off so that hopefully when those two users try to jump back on, because of their random back-offs, they'll not clobber each other again. I just thought of what it is. It's called CSMA, Carrier Sense Multiple Access with collision avoidance. So they add another acronym on there, CA, CSMA with CA for collision avoidance. And that's kind of a basic model in Wi-Fi and in Ethernet. So you're queuing with your random back-off, and of course if you get thrown off a second time, you repeat that. You just keep trying over and over again. And that's why sometimes you feel like you're getting choked, because everybody wants to get on and they're all randomly backing off. So queuing theory from mathematics tells you that as the network gets more congested, the mean time to wait, rather than staying like a nice linear progression as number of users grows, it grows exponentially. As the number of users come on, it doesn't just grow linearly, it just goes exponential, because all of this thrashing that goes on eventually just drives the time up to infinity rapidly. You've experienced that, right? Like on a Wi-Fi node, they limit how many people can get on just because they're trying to keep those people that are already on with satisfaction and not let anybody else on. Does that sound fair? You were there first, right? And they're wanting to have a certain quality of service for you, and then you have to get off before another person would be allowed to be admitted. There's all kinds of strategies, of course. EEs do that sort of protocol, and quality of service type stuff, but computer scientists are also involved with that part of things too. And those, of course, are built into standards. So when you buy something, it has that standard that it adopts. Well, here's an example of very physical level development. This was a project I worked on during my sabbatical in 2005, 2006, when I was at Real Time Logic. We published a paper. I did a really high fidelity model of a satellite communications link. It's a relay link. And so this block diagram appeared in the paper, and it's just showing what some of the digital modulation schemes were, but the idea of me showing it to you is it's just showing you that there's a transmitter, there's various impairments that I had to model in the system, there's some filtering that was band limiting the signal, so it was causing distortion. We were trying to send a lot of bits per second per hertz of bandwidth through, which is a measure of efficiency, how well, you use the allocated spectrum. You'd like to put through lots of bits per second per hertz of bandwidth, because then you're making use of the spectrum as best as possible. But then there was a high power amplifier, namely a traveling wave tube amplifier, that runs at close to saturation, so it introduces some other types of distortion. It introduces primarily what's called AM to AM and AM to PM, because of the nature of the amplifier as it's going into compression. Now I know that sounds really far out to you, but you've built audio amplifiers in electronics, right? No? Just a single transistor amplifier that you put a signal in and you look at the signal that comes out? Well, those of you that are seniors have done that. When you tested your amplifier, did you put the sine wave in until it no longer looked like a sine wave on the output, just to see where it starts compressing or distorting? Well, if you were to get to the nitty-gritty of the amplifier, when it's going into that compression mode, it starts to go nonlinear, and what happens is, so you're getting this AM to AM, which is an amplitude type distortion because it's starting to saturate. But the nitty-gritty of that for microwave type amplifiers is the phase starts shifting in a nonlinear fashion as it goes into compression. And if your signal is phase shift keyed modulation, then that amplifier starts messing around with the way you're sending information over the carrier. If you're relying on the carrier phase being 0 or 90 degrees, switching back and forth for the information, and if the amplifier is starting to twist it just because of the compression, then that imparts more performance impairment. So that was built into this. And then that was done on the transponder up in space, and then it comes back to a receiver on the ground. So the solution of the project was to build what's called an adaptive equalizer, something that will try to undo some of the distortions. And to make it be flexible for different environments, it was made adaptive so that it can automatically design these FIR filters on the real and imaginary parts of the signal to try to mitigate some of that distortion. Now everyone in here is at least from 2610, you've heard of FIR filters, right? This was implemented using an FPGA. I did simulations in MATLAB, and then the guy that coded up the FPGA was another member of the team. And then there were other parts of the system too. So this was our adaptive equalizer. Actually, the guy that did the coding is this guy right here, who works for another sister company now. So he's not here in town at RT Logic anymore. So when we were looking at a performance measure, one thing is this scatter plot, which should be 4 dots on the page for the modulation scheme, 4 tight little clusters, but the distortion was making them get kind of distorted. And I called these guys here, I called them jelly beans, even though they were ellipses. I just said they looked kind of like jelly beans from the side. That's what I referred to them as, and they were canted in those angles like that. The equalizer came along, and it didn't totally get it down to a dot. It would have liked to have gotten 4 dots right here. But it did make them look more circular and did compress the distortion. In terms of the way you measure performance on a digital communication link, it's the error probability versus the received signal-to-noise ratio. So we were measuring the probability of a bit error, and we were trying to operate at a 10 to the minus 6th error probability level. Those of you taking probability or had probability, I mean, communications theory uses lots of probability models and randomness. Not in this first semester, but in this Com2 class. So without the equalizer, we were operating way out here with that distortion. With the equalizer in this preliminary model, it pulled in by about 8 dB, which is quite a good improvement. Okay, last and final example that I put in the notes, which was just last year. I was reading an article in an online journal. I thought this was pretty cool. A wireless in the eye. Now, I was wearing contact lenses until I had to stop because I needed to start to wear the glasses to see the computer better. I just was getting too fatigued with my contacts. So I got pretty good, and some of you are really good at taking a lens in and out of your eye. Some of you don't want to do that at all because you don't think anybody should touch their eye at all. Well, think about putting a piece of electronics in your eye. That sounds, like the ultimate. Well, you can see the picture there, how big it is. It's pretty tiny. And the design was for measuring eye pressure. How many of you have ever heard of glaucoma? It's a very serious progressive disease that eventually leads to blindness. So managing it early on is one of those things that they try to do. So this was designed to be a glaucoma pressure sensor. And the article was primarily about energy harvesting, but it also has the radio part. So the system block diagram is light comes in, whether you're outside or inside, and can charge the battery. And then periodically throughout the day, the patient would, my understanding is they would get something up close to their eye that would be the transmitter, and then it would bounce in, not powering the device, but the battery power would wake up the microcontroller, tell the transmitter to send pressure data out, and then gets logged. My understanding is that it would be for a patient that's being monitored for their glaucoma, and I don't know all the details. I have a close friend that has it, and I know it's been pretty devastating for him. It doesn't happen just like that. It's just he continues to get worse and just can't see really well. But he only gets his measured when he goes to see his eye doctor, so this would allow more progression, and I think things change between day and night, so that's what this project was about. So these are just some of the facts about it. I guess I said every 15 minutes is what the article said they measure pressure, and how much energy can be stored in the battery, and how much power is used on average when it's transmitting. That's the size of the battery there on the dollar bill, and then next to it is the layout of the packaging and everything. Maybe someone of you will be involved with some medical applications, because wireless is pretty pervasive in medical. Well, at the same time, people wonder about what does RF do to our cells and other things. Has anybody ever read up on that? No?
Cell phones next to you.
Yeah, exactly. It's non-ionizing, so it's low enough density. It can cause some localized heating, but I know that there are people that also speculate that it's doing some other things that aren't official, that aren't really well understood yet. Just something that we as electrical engineers have to be aware of, because health and safety is something that we have to be aware of. It's not clear right now. So no one in here has really taken an interest in that, or on the side wondered? Yeah. I mean, I think of the case of cigarettes and cancer. I mean, a long time ago, people didn't think that caused cancer, right? And it took a very, very long time to finally make things more concrete. And then it was kind of a, the way it came out and the way the companies, the tobacco companies, kind of hid certain things. But, are we going to, as electrical engineers, if something becomes concrete, what's going to happen in the industry? I'm sure no cellular provider wants to not sell their products. So it's just part of being responsible. When you take 4890, we talk about that for sure. Any questions before I jump into chapter 2? Okay, getting into our review of linear systems, we're going to start really simple with signal models. So a fundamental model that we use over and over again and is fundamental to communications in free space at least is a sinusoid. So a sinusoid has three main parameters in it. It has its amplitude, which I've got written down here as A of t. It has its frequency, and it has its phase. When you first learn about the sinusoidal signal in 2610, those three are constants, right? You remember from back then? Just a sinusoidal signal sits at a fixed frequency, at a fixed phase, and at a constant amplitude. But now in this class, this is the big deal. We can make all three of those be functions of time. Not necessarily all at once, but if we want to do a type of modulation called amplitude modulation, we make A a function of time. If we want to do frequency modulation, we make F0 a function of time. And if we want to do phase modulation, we make phi a function of time. I'm not going to do that on the next page, but that will be coming up in Chapter 3. So it's definitely important that we know about sinusoids. For right now, though, this is a deterministic sinusoid, meaning that it's a completely specified function of time in our modeling. In actuality, though, in a communications application, that's never the case. It's just that we can look at it deterministically for a certain type of test waveform. But as a practical matter, it will never be deterministic. And a fundamental reason why that would be is if we're going to send useful information from point A to point B, doesn't it have to be random? I mean, if it's going to carry information, if it was always deterministic, what knowledge would be conveyed if it was the same thing? I mean, even if you start saying I'll send a 1 some of the time and a 0 another some of the time, those still have to switch back and forth kind of at random if it's going to represent information. So I'm not trying to get you perplexed. I'm just trying to make you think, you know, that will be a factor. But we're going to stay out of random signals, basically, except, like I said, in simulations. Random signals are kind of the opposite, where the outcome is a function of some underlying sample space from probability theory. Now, because there's graduate students, juniors and seniors in here, some of you are probably just now taking 3610, right? Is anybody taking it right now? Okay. And the rest of you had it last year, probably. So I can't get too carried away, but you're going to be coming along in that class, and I can throw a few things out if it's relevant, but this class is void of probability officially. Then there's other classifications that come in once we start talking about signals. And when we look at a sinusoid, if it's got fixed frequency and phase and amplitude, then we can remember that it's a periodic signal. It obeys this property. Periodic signals are such that you can take the waveform, pick it up, and slide it over, and it can drop on top of itself, and it matches. That's what this idea of periodic is. And the other thing about a periodic signal is, for that to be possible, you generally will have to think that t is going to be over all time, if it's truly periodic. Aperiodic signals are something that comes and goes. It just occurs once, maybe it occurs 10 times in a row and is gone. It's just another form of model. And in the world of deterministic signals, you can say as one type of classification, and there's many different ways of classifying signals, and they're kind of overlap each other. If a signal is not periodic, then it's aperiodic, because it breaks down in that classification as being one or the other. But then we're going to get in another page or so, a signal can be an energy signal or a power signal or neither, and that's another way of classifying a signal. And it's confusing, I know, because this is what I've been writing in my book, and my editor, who's not an engineer, when I wrote all this stuff down, she tries to understand it, because as I've learned, a dummy's editor is supposed to be the advocate for the dummy that reads the book. I'm not saying that in a negative way, because that's the way the books are written. So she's trying, she's an English major, and she's trying to understand my stuff to be an advocate, and she got really confused, and I just, it was like she's convinced I was doing this all wrong, and of course it made me mad, because it's like, I know this stuff and you don't, but she's just trying her hardest to understand it, and it can be confusing though, right? There's also a picture of a random signal on here, and I would associate that signal with what? Noise. That's what you want to just call it. It's noise. So this is also the terminology the book uses for this rectangular pulse signal. So this definition is this picture. I realized that I don't have another common pulse signal in here that we use a lot, and that's the triangle signal, T over tau. And the picture of that signal is this triangle that starts at minus tau and goes to plus tau, amplitude 1. It gets defined eventually later in the notes, but the very first homework problem uses this signal, right? If you looked at them. Okay, now we get into some other aspects of signals, namely what are called phasor signals and the spectra. And the phasor signal sounds pretty sophisticated, but it's really just a complex sinusoid. The phasor idea from way back in 2610 was that you could take this complex sinusoid and you can break it up into two pieces, the phasor part, or the fixed phasor portion and the rotating phasor portion. So the e to the j phi is fixed, and then this is the function of time. So it's like if you were to do snapshots, you've got this a e to the j theta, and then it's sitting multiplied times this e to the j omega naught, which is the thing that's always spinning around. I guess it spins around, from your perspective, counterclockwise. And of course, you ran into this in circuits. It's just a convenient representation, and to get more detailed on that, the phasor spins at a rate of omega naught radians per second. If I divide that by 2 pi, I get the frequency rate, and if I take the inverse of that frequency, I get the period t naught. So it's t naught seconds is the time it takes to spin once around in the complex plane. And there's a picture of it down here from the book again. So this is the rotating phasor idea. And of course, if you take the real part of the rotating phasor, you get the cosine back. So this picture is showing you the phasor rotates around, and if you project it onto the real axis, that gives you the cosine wave. If you project it onto the imaginary axis, that gives you back a sine wave. And now that you have the real cosine back again, you can take and turn this whole thing around and say, well, remember from Euler's identity that you can expand cosine out into two complex exponentials, one that rotates counterclockwise and the other one that rotates clockwise. And then there's that 1/2 factor in there, which is the way Euler's identity works, or Euler's formula works. Right? Is this familiar? So this is probably what we're going to be working with quite a bit here in this review. The idea that we can write a cosine as two complex sinusoids. And this is the basis for getting the the spectral representation underway. And why is the spectrum so important? It's because what we already talked about, we want to know where our signal sits spectrally. So the simplest signal to develop a spectral concept of is a sinusoid, because it has a single frequency, as long as that's not time varying but fixed. And the way we get the spectral representation is from this expansion into two complex sinusoids. We say that a real sinusoid is composed of a frequency at plus omega naught and minus omega naught. And that's on this next page. This is the so-called two-sided line spectra that I'm hoping you remember something of from 2610. So the sinusoid is sitting at a frequency f naught. That's one of its parameters. So the spectral representation of that time-varying, the sinusoidal waveform, which goes up and down, the other view of it, the frequency domain view, is it's composed of a spectral line on the frequency axis at plus and minus f naught, and its amplitude is 1/2 a, because of Euler's identity, saying that you decompose a cosine into 1/2 a e to the plus j omega naught and 1/2 a e to the minus j omega naught. And then the phase, which was in the argument of the cosine, pops up as a phase spectral line at plus and minus f naught, again from this expansion. So you look in here and there's like a plus sign there. So the frequency domain view of this x of t is to say that if I go ahead and sketch the spectrum like is on the other page, I say that the magnitude spectrum is, got these two spectral lines, because I see that when I expand it off, I get the a over 2, and I get the minus f naught and the plus f naught. And then the other line spectra is the phase, which instead of, it pulls out the phase of the argument. So this other piece of information, theta, plus and minus theta, is used to create this plot right in here. And really, there's not anything more you can do with it. It's like we've mined out all the useful information in this frequency domain representation. We've got the amplitude versus frequency. There's a complex sinusoid positively spinning at f naught, negatively spinning at minus f naught. And associated with those two frequencies, there's also a phase of theta and minus theta. It doesn't seem all that thrilling, but it is what it is. I mean, that's just getting the expansion to look at it in the frequency domain. But it's a start, because if that's the carrier of our wave that's going to carry our information, we can see that it's centered right at f naught. Now, the positive and negative frequency idea is essential for the mathematics to work, as demonstrated by Euler's identity, expanding it in that fashion. We can't really get a workable theory if we try to ignore the negative frequencies. But from the standpoint of displaying something and wanting to look at it in the laboratory, we know that if we have a function generator producing a cosine, that knob stops at 0. It doesn't go to a negative frequency. And going to a negative frequency really wouldn't bias anything, because we know that when we expand out cosine, we get the positive and negative, so we gain nothing. Now, in the world of digital signal processing, you might want to have a negative frequency, because then you might have a complex sinusoid, period, never a plus and a minus spinning at the same time. So, not trying to get you too confused, it is possible from an instrumentation standpoint to just look at what's called the single-sided spectrum. And what it does is it displays just the positive frequencies. The phase stays just like it is over here. The amplitude, though, is doubled to basically bring things into calibration. Rather than having a line at minus f naught and plus f naught, it puts a single line at f naught, and then it has to represent it with doubling of the amplitude to be calibrated. Those of you that are in the lab, when you work with the spectrum analyzer in Lab 1, this is the mode you're going to be in. The spectrum analyzer displays actually it displays only the amplitude spectrum. It doesn't do the phase. And it's calibrated to be a single-sided spectrum. So you don't have to worry about dividing by 2 or anything like that, or multiplying by 2.
Question. So do both of these convey the same information?
Mm-hmm.
Different? It's dependent upon how you view it?
Exactly.
Okay.
Now, if you're smart, you're probably saying, why do I need the two-sided? Because it's redundant information. I mean, if you have the single-sided spectrum, you still have the information that was in the original time signal. You have the F0, you have the amplitude and the phase. That's true. And that's because it's a real signal. A real cosine wave will always, due to the symmetry, and we're going to see that in a second, will always break out like this. But in communication, signal processing, you may have actually a complex signal, and then this symmetry doesn't hold anymore. That's not something we're going to do in this class, except when we get to the Hilbert transform, we'll see it in there. So it puts me in an awkward position to make a good cell, if you know what I mean. I can't really convince you why do I have to have something more complicated when it seems like something simpler is sufficient. But on the other hand, you're old enough to know from taking calculus and other math classes that sometimes things just have to be complicated for reasons that you can't fully appreciate until you get far enough down the pathway. And if I was to cheapen it up right now just for convenience, then it would come and zap you when you needed it. So I can't do that. We were having a discussion in the faculty meeting this morning about some things I won't elaborate on, but Dr. Wong at one point said, just make it easier. He was just joking around. He was like, stop the students from complaining, we'll just make it easy. But you don't really want us to do that, right? Because if that's what you need to know to do your job, it's like you'll feel really bad when you're next to somebody from another school that learned it the right way, and if you didn't learn it the right way, you'll feel like, I got ripped off. They didn't teach me what I needed to know. I want my money back or something. So sometimes, though, in life, we want to cut corners because we're exhausted. In this case, I'm not going to cut that corner. So we're going to stay with a two-sided spectrum most of the time, but when you're in the lab, you're going to interpret it as the one-sided because that's what the instrument does. So a little review example would be this multiple sinusoids case, and this is like a homework problem from 2610. We are given two cosines, one at 10 hertz, one at 100 hertz. You've got some phases in there, and you've got some amplitudes. So the idea is to sketch out the two-sided amplitude and the two-sided phase spectra for this signal. So when you first got introduced to this in 2610, you factor out the cosine using Euler's identity. So for this first cosine wave, I go down here and expand it like that. For the second cosine wave, I go down here and expand it like that. So why the 2 and the 12? Remember, Euler's identity has that 1/2 in it, so that's why I had to divide through by 2. Other than that, the information is there. It's redundant like we were just talking, except we have a positive and negative spinning complex sinusoid. And the way I like to think of it as I see the amplitude sitting there, I see a 2 right here, and I know that 2 is going to sit at a line at 10 hertz and also a line at minus 10 hertz, right? Then I go down here and I see a 12, and I know that that's going to sit as a height at 100 and a height at minus 100. So that gets my magnitude or amplitude. And let me just, since my editor, I'm really fresh with ideas from my editor and what caused lots of frustration. She said one time, explain to me, Mark, why you use amplitude and magnitude interchangeably. Why do I? Well, because books do it that way and people talk that way. Magnitude is really the proper way. When you have a complex quantity, don't you think of magnitude? Magnitude would be like the square root of the sum of the squares. Amplitude is kind of sloppy sounding, but it seems to be what people like to use, though, for spectra. So amplitude you can think of as being just sort of the slang version of magnitude. Magnitude would be the more mathematical way. What's the magnitude of a complex number? At any rate, so I have enough information to do the amplitude or magnitude line spectra, and then I can get involved with, you know, those guys with their minus signs, and I have to carry the minus sign through on these two for the phase spectra. And that's right, sketched right over here. Any questions on that? I mean, I thought about I could bring in a worksheet and I could pass out you a blank sheet and draw, and I may do that sometimes too, because I was taught principles of active learning at a workshop I went to once in signal processing community put on. And sometimes active learning is important. I mean, I was told it was always important. People are active learners, so if I give you a blank sheet and make you do something, then it can be more impactful than just watching me do it all the time. So I'll maybe think about doing that on occasion, especially if I think some people are not getting things. Engineers don't like to do active learning in the classroom. Probably LAS likes to do active learning best of all. Some of you have been exposed to that, right? Part of the rule of that is to make you feel uncomfortable. In a sense, that's kind of one of the themes of active learning. You need to make individuals have to perform on the spot. And I know we don't like feeling uncomfortable, right? Especially in a group. Okay, so the next things are singularity functions. I'm going to time out here very quickly. I think what I'd like to do, just so that you can go look at some things, because I really haven't gotten into the homework problems. This is the second of a couple of homework problems, but what I want to go look at is, after singularity functions, there's going to be a little discussion on another type of signal classification, namely energy and power, that I don't think we do in 2610, but I think you do in 3205 maybe. Where did you first see this? Because I don't remember. 3205? Yeah, power signal. Well, you're in the lab and you want to, even in circuits, I mean this applies to circuits, this is where I first learned it in a circuit. How much power is delivered to a resistor sitting in some branch of a circuit? Well, so here, yeah, instantaneous power is what? It's right here. E, which is voltage times current. So then we have these definitions of energy and average power. And when you work the very first problem, and I've already posted the solutions up there, I don't know if anybody noticed, but they're up there. I need to give you the password, which I haven't done, which I didn't bring my cheat sheet down here, but I think I can remember it. It's written on a paper in my office. There's another definition, though, that's very useful here, and that is that if periodic, you don't have to do this limit. You can just do 1 over t times the 1 over t naught, and then integrate over a period, say 0 to t naught, of magnitude x of t squared dt. And to kind of take you on a little visit of that, I can go into the solutions that I've put up. Okay. This very first homework problem has to do with a train of triangle pulses and wanting you to find the power in that signal. So the way I find the power in that signal, and there's a square that some reason or another is missing, I take the magnitude squared of that signal and integrate it over one period, which for this signal that would be from here to here, but I'm not integrating anything useful except on the interval -2 to 2. So that's why the integration limits go from -2 to 2. And because you have to square it, that triangle becomes a parabolic shaped thingy. And another thing that happens from symmetry, what can you do here? You could do 2 over 5 and then integrate from 0 to 2. And now it's going to be a little bit more manageable because you just have to integrate that. And that's a polynomial, and that's the simplest type of thing to integrate. I've got oodles of demos. I have ADS ready to run here, and Mathematica, and run MATLAB, but I'm not going to be able to do that today. So we'll just see where we're going to get. Remember I said the philosophy for heading for this first quiz next week would be that I will pull things off, depending upon what we've covered through Tuesday. I will look at it, I will do an assessment, and then I will make a call as to what the first quiz will be over. If we can't get through everything, because I really don't know. I'm going to try to look at the sheets the surveys, and just see what some of the concerns are. As I look around, I don't see anybody looking really nervous, but that doesn't mean that you're not worried. It seems like there's less people here today, so I don't know whether that meant that everybody was going to watch it on video that wasn't here today, or whether they've all dropped. I just don't know. So, have a good weekend. And if you're in 4890, which I know some of you are, I'll see you tomorrow morning at 8 o'clock. Don't be late. What's that?